When people say Windows, they usually mean the desktop you see. The Start menu, the taskbar, File Explorer, all the stuff you click. But if you want mastery-level understanding of Windows, you have to stop thinking about it as a user interface and start thinking about it as a layered system. A kernel, a security model, a process model, a file system model, and a compatibility model that has been evolving for decades. Windows is not just an operating system. It's a long-running contract with the past. And that contract shapes almost every design choice Windows makes. A good place to start is something most people misunderstand from day one: file types. On Windows, file types in the everyday sense are not a property of the file itself. On Linux, the system often cares about what's inside a file or the permissions on it. On macOS, file types can be tied to metadata and application bundles. But on Windows, the thing most users call a file type is usually just the file extension, like .txt, .jpg, .exe, .dll, etc. Windows uses that extension as a hint for what program should open it and what icon it should show. That mapping is mostly handled through file associations, which are stored in the system configuration rather than inside the file. That's why you can rename a file from a .txt to .jpg and suddenly Windows thinks it's an image. The underlying bytes didn't change, but Windows changes its assumptions because the extension changed. This is one of the reasons double-click behavior is more about configuration than content. When you hear someone say, Windows is insecure because file extensions can be faked, what they really mean is that Windows leans heavily on user-facing hints. Modern Windows has mitigations, like showing file extensions by default in many configurations, and security checks that don't rely on icons. But the core idea remains: file extension is a UI-level convention, not a deep truth. Now, beneath file types is the real foundation, the file system. On modern Windows, the default file system is NTFS. NTFS is one of the most important reasons Windows behaves the way it does. And it's a major difference between Windows and many Linux setups. NTFS is not just where files are stored. It's a database-like structure that supports permissions, auditing, encryption, compression, quotas, hard links, alternate data streams, and journaling. The journaling part matters because it helps keep the file system consistent after crashes and power loss. NTFS tracks changes so it can recover gracefully. One of the most Windows features in NTFS is access control lists, or ACLs. Linux has permissions too, but the Windows security model is deeply tied into the file system. In Windows, permissions are not just owner/group/other read-write-execute. They're fine-grained rules that can allow or deny specific actions to specific identities. And those identities don't have to be local users. They can be domain accounts, groups, system identities, services, or built-in principals. This matters because in Windows, the file system is not just a storage system, it's part of the security system. To understand Windows, you also have to understand that paths are more complicated than they look. Windows has drive letters like C and D, which people often think are physical disks. They're not necessarily. They're mount points assigned to volumes. Windows also has universal naming convention paths like server/share/folder, which represent network resources. Windows tries to unify local and network access in a way that feels consistent to users, but under the hood, file access might mean local disk, remote SMB share, or even a virtual file system backed by something else. Windows also has a famous directory structure that people see but rarely understand. C/Windows is not just where Windows lives. It contains the core operating system files, but it's also shaped by decades of compatibility requirements. Within C/Windows, you'll see System32, and that name is one of the most misunderstood artifacts in computing. Many people assume System32 contains 32-bit system files. On a 64-bit Windows system, System32 actually contains the 64-bit system binaries. The 32-bit binaries often live under syswow64. This inversion exists because of compatibility. Countless programs hard-coded paths to System32, and Microsoft chose continuity over cleanliness. That tells you something fundamental about Windows. Windows will bend reality to keep older software working. That compatibility story is everywhere. Windows supports a huge range of legacy APIs and behaviors. It's one reason Windows dominates enterprise environments. You can run a weird line of business app written 15 years ago, and it still works. But it's also why Windows can feel complex compared to cleaner systems. Now, the OS, in the deep sense, is not the file system. It's the kernel. Modern Windows is built on the Windows NT architecture. The NT kernel is responsible for core operating system functions: scheduling, memory management, hardware abstraction, I/O, security enforcement, and process thread management. It's designed to be a general-purpose kernel that can run on different hardware and support different subsystems. In Windows, the kernel is not a monolith in the sense people sometimes describe Linux, but it's also not a pure microkernel either. It has a hybrid architecture. Some components run in kernel mode because performance and control matter. Other components run in user mode to improve stability and security. When something crashes in kernel mode, it can bring down the whole machine. When something crashes in user mode, the OS can usually isolate it. This user mode versus kernel mode boundary is essential. Kernel mode has full access to hardware and memory. User mode is restricted. The boundary is enforced by the CPU itself using privilege levels. Windows leans on this boundary heavily, and a lot of security features are about tightening it further. Now let's talk about how Windows runs programs. On Windows, the basic unit you interact with is a process. A process is an isolated container for a running program. It has its own virtual address space, handles to resources, security identity, and one or more threads. Threads are where execution actually happens. If a process is a container, threads are the workers. Windows schedules threads, not processes. When you see a process using CPU, it's actually one or more threads running. Windows uses preemptive multitasking. That means the scheduler decides which threads run and for how long. Threads get time slices. The scheduler considers priorities and fairness. Higher priority threads run sooner. Real-time priorities exist, but are dangerous because they can starve the rest of the system if misused. If you want mastery in Windows, you eventually have to think like the scheduler. You need to understand why a system feels frozen even when CPU isn't maxed, why I/O-bound workloads behave differently than CPU-bound workloads, and why background services sometimes steal responsiveness. Windows also has a very mature I/O subsystem. A major design feature in Windows is that many operations are asynchronous and event-driven under the hood. Even if you write code synchronously, Windows often supports overlapped I/O and completion ports, which allow high-performance servers to handle massive numbers of connections efficiently. This is one of the reasons Windows can run heavy enterprise workloads. The underlying primitives are robust. Now let's move into memory, because memory is where operating systems get interesting fast. Windows uses virtual memory. Every process thinks it has its own continuous address space. In reality, that address space is mapped to physical RAM and to disk-backed storage, such as the page file. Virtual memory enables isolation. One process can't simply read another process's memory. It also enables overcommitment. The system can pretend there's more memory available than physically exists, as long as not all of it is actively used at once. When memory pressure increases, Windows pages memory out to disk. That's why a system can become painfully slow while still showing some free RAM. It's not just about how much memory exists. It's about how memory is mapped, cached, and reclaimed. Windows also heavily uses caching. The file system cache is a big deal. Windows tries to keep frequently accessed file data in memory because disk is slow. That means free RAM being low is not necessarily a problem. Unused RAM is wasted RAM. The problem is when the system starts thrashing, paging in and out constantly. Now, one of the most unique and controversial aspects of Windows is the registry. The registry is a hierarchical database that stores system and application configuration. Instead of scattering configuration across many text files the way many Linux systems do, Windows centralizes large portions of configuration in the registry. This has real advantages. It can be queried efficiently. It supports permissions. It can be managed centrally in enterprise environments. It allows consistent configuration APIs, but it also has downsides. It can become messy. Uninstallers leave debris. Debugging configuration issues can feel like archaeology. And because the registry is so central, corruption can have serious consequences, though modern Windows is far more resilient than older versions. If you want a practical mental model, think of the registry as Windows' configuration backbone, tightly integrated with security and policy. It's not just settings. It's part of how Windows enforces behavior. That leads naturally to services. A lot of what makes Windows feel like Windows happens in services. Services are background processes that start automatically and provide system functionality. Networking, printing, updates, authentication, event logging, many of those are services. The service manager controls them. Services can run under different identities. Some run as local system, which has enormous power. Others run under restricted identities. Service isolation and privilege reduction are major parts of modern Windows security hardening. Now let's talk about security, because this is where Windows differs sharply from many people's assumptions. Windows security is identity-centric. At the heart of it is the concept of a security principal and an access token. When you log in, Windows creates a token that represents who you are and what groups you belong to. That token is attached to your processes. When a process tries to access a file, a registry key, a network resource, or another protected object, Windows performs an access check using the token and the object's ACL. This means security is consistent across the system. Files have ACLs, registry keys have ACLs, even kernel objects like events and mutexes can have security descriptors. The model is pervasive. User account control, or UAC, is another crucial piece. UAC is often misunderstood as a nag screen, but the design goal is actually separation of privilege. Even if you are an administrator, your processes typically run with a standard user token by default. When something needs elevated privileges, Windows prompts and creates a process with an elevated token. This reduces the chance that everyday applications run with full admin rights. It's a compromise between usability and security. Not perfect, but it has significantly reduced the damage that malware can do compared to the everyone runs as admin era. Windows also has modern security features like code integrity, driver signing, secure boot, and virtualization-based security. These are part of a broader trend. The OS is not only isolating processes from each other, it's increasingly isolating the kernel from certain kinds of attacks and isolating secrets from the rest of the system. One of the key differences between Windows and Linux here is the enterprise identity ecosystem. Windows integrates deeply with Active Directory and domain policies. That matters because in many real environments, Windows security is not just local machine security. It's identity and policy at scale. Group policy, Kerberos authentication, domain-based access control. Windows isn't just protecting one device. It's designed to participate in a managed fleet. macOS has its own enterprise story, but Windows is still the default in many organizations because this identity-first design has been built up for decades. Now, you asked about system files and what they do. In Windows, system files include executables, dynamic link libraries, drivers, and configuration components. Executables like Explorer.exe are part of the user shell. Many critical system services run as svc host.exe processes, which host Windows services. That can look suspicious to beginners because you might see many instances of svc host.exe, but it's normal. It's a service hosting model. Multiple services run inside service host processes for organization and efficiency. DLLs are another major concept. Windows uses dynamic linking heavily. Many applications rely on system DLLs. That's part of why Windows has historically had DLL hell, where version mismatches cause chaos. Modern Windows has improved that with side-by-side assemblies and better packaging, but dynamic linking remains central. Drivers are kernel mode components that interface with hardware. Windows enforces driver signing on modern systems to prevent untrusted kernel code from being loaded. This is one of the biggest security lines in the sand. If malicious code runs in kernel mode, it can bypass most protections, so Windows treats kernel mode code as highly privileged and tightly controlled. Now let's compare Windows to macOS and Linux in a way that actually matters. Linux is often described as everything is a file. That's a worldview. It means devices, processes, and system interfaces are often represented as files under virtual file systems like /proc and /sys. Configuration is usually text-based and scattered across /etc. The philosophy favors composability and transparency. Windows has a different worldview. Windows favors centralized APIs, object managers, registries, and policy-driven configuration. Instead of representing everything as a file, Windows represents many resources as kernel objects accessed through handles. Instead of editing text files, Windows often expects configuration through system APIs, the registry, and enterprise policy tools. macOS is built on Unix foundations like Linux, but it also has Apple-specific layers and a very controlled hardware ecosystem. macOS benefits from tighter hardware integration and a narrower compatibility surface. Windows supports an enormous range of hardware and legacy software, which makes it more complex, but also more universal. So what makes Windows distinct? It's that compatibility and enterprise manageability are first-class goals. Windows is an OS designed to be installed on almost anything, run almost anything, and be managed at scale. If you're aiming for mastery-level knowledge, the final piece is understanding how to observe Windows rather than guess. Tools like Task Manager give you a surface view, but deeper tools like Process Explorer, Performance Monitor, Event Viewer, and Windows Logs show you what's really happening. Windows is instrumented heavily. Events, logs, metrics, traces. When you learn to read those signals, Windows stops feeling mysterious. At mastery level, you stop asking, "Why is my computer slow?" and start asking, "Is this CPU scheduling pressure, memory paging, disk queue depth, network contention, or a service loop?" You stop treating the OS as a black box and start treating it as a system with measurable behavior. Windows mastery is not memorizing file paths or registry keys. It's understanding the model, how Windows represents resources, how it schedules work, how it enforces security, and how it trades simplicity for compatibility. Once you adopt that model, Windows makes sense, not because it's simple, but because its complexity becomes coherent. And when an operating system becomes coherent, you stop fighting it. You start using it intentionally.